Alright, guys, boleh nampak slide ya?
Nampak.
Okay, alright. So sorry, kering tekak lah. Alright, so now we continue. So that's the different type of beam. Okay, so we have simply supported beam, overhanging beam, and also cantilever beam. Alright, so now internal shear force and also bending moment diagram, sign convention. Okay, so alright, so in order to analyze the beam, okay, so let's say we are doing the sectioning. Okay, sectioning in order to calculate the internal shear force and also internal bending moment. So we have to do the sectioning. Okay, so let's say we do sectioning at point A. Okay, point A, and then we take the left part of the beam. Okay, so means we do the sectioning at point A, and then we analyze the left part here. Okay, which is here. Okay, so as I said, the beam is subjected to once the beam is subjected to load, so the internal, okay, so once we apply the load, so it will develop the internal shear force and also internal bending moment. Okay, so that's why if you see here, okay, if we analyze the section at point A, so you will have shear force. Okay, so this is the internal shear force. Internal means we do cutting and then we can see this force. Okay, so this force basically is inside the beam. Okay, and then we also have the bending moment, so MA. Okay, so same thing to point B. If we do the sectioning and then we analyze the left side of the beam, okay, so that's become this one. So we have internal shear force and also internal bending moment. Okay, so to make it standardized, okay, to make it everybody do the same direction of the internal force, if you analyze the left side of the beam, okay, so please draw the shear force, the internal shear force downward. Okay, the direction of the shear force will be downward, and then the bending moment should be counterclockwise. Okay, if you analyze the left side of the beam. Okay, so same thing here. So the internal force, the direction is go downward, and also the bending moment is counterclockwise. Okay, so that's what we call as a sign convention. Okay, so we make it standardized. Everybody will do the same direction, so that it is easier to marking and so on. Okay, even this direction has been used for everyone. Okay, everyone use the same direction. Okay, so same thing to point C. But you can also analyze the beam from the right. Okay, from the right. For example, if I do the sectioning at point C, so if you take the left side, it's become like this. Okay, you have to analyze this part, okay, which is here. But if you do the sectioning at point C, and then you want to analyze the right side, also can, which is here. So we do the sectioning at point C, and then we analyze from the right side. Okay, from the right side, which is here. Also can. Okay, also can. But the direction of the shear force will go upward. Okay, the direction of the force is directed upward. Okay, and then the direction for the bending moment is clockwise. Okay, clockwise. So please, okay, if you analyze the beam, if you want to analyze the right part, use this sign convention. If you want to do from the left side, use this convention. Okay, otherwise your result is slightly different with others. Okay. Alright, so this is the example. You have a beam. Okay, you have a beam, and then subjected to load P2, P1, and also distributed load. Okay, so this is distributed load W, P1, and also P2. And then let's say we do the sectioning at point C. So if you analyze the left part of the beam, so you see the shear force is directed downward, and the bending moment is directed tend to rotate in counterclockwise. Okay, but if you analyze from the right part of the beam, if you analyze the right part of the beam, okay, so the shear force will be directed upward, and also the bending moment will be clockwise. Okay, clockwise. So that is the standard sign convention. Okay, you can see here, left this direction, right this direction. Okay. Alright. So now we proceed with the method of section. Okay, so this is the method. This is the procedure. How to draw. This is the procedure on how to draw the shear force and also bending moment diagram. So there are 4 steps. Okay, I hope you follow one by one when you are trying to draw the shear force and also bending moment diagram. Okay. Okay, remember, so this is the step to draw the shear force and also bending moment diagram according to method of section. Okay, so first you have to draw the overall free body diagram. Okay, for example, I give you one simple example. There is the beam, and then the beam is supported at point A and point C, for example, and then subjected to load P, okay, which is at point B, for example. Okay, so that is the question, for example, simple question. So the first step, draw the free body diagram of the beam, overall free body diagram. So means that we have to draw the free body diagram, which is in step 1. So we draw free body diagram. So this is support A. So this is the pin support, so we replace by FA, reaction force, and then this is the roller, so we replace by reaction force at roller, and then of course we have load P. Okay, so let's say the distance here is 2 meter, and then the distance here also 2 meter. Okay, remember, free body diagram should have the external force, internal force, okay, or reaction force, and also the distance. So that will be the complete free body diagram. Okay, so again, complete free body diagram should have internal, external force, reaction force, and also distance. Okay, so that is the step 1. Step 1, draw the overall free body diagram, and then convert distributed load to equivalent concentrated load. Okay, so this is the case if you have distributed load. Okay, for example, the same beam, but subjected to distributed load. Okay, for example, you have distributed load. So the first step, what you have to do is, so this is the case of concentrated load, so no need to convert, okay, from distributed load. But if you have the concentrated load, so what you have to do is you convert the distributed load into concentrated load. Okay, so you will have the FA, and then FC, and then FW. Okay, FW. Okay, so you convert from distributed load into concentrated load. How to convert? I will explain in the next slide. Okay, I will explain in the next slide. And then number 2, okay, number 2, determine the reaction force at the beam. Okay, so that is the step 1, draw the free body diagram. And then step 2, determine the reaction force. Okay, so we have to determine the reaction force, so that will be the step 2. Okay, alright, and then analyze each section of the beam and determine the mathematical function between shearing stress S and also bending moment X. Okay, so step number 3 is analyze each section. Okay, so what we have to do is we do the sectioning. Okay, we have to do the sectioning for each section. For this case, we do sectioning for AB and also BC. Okay, AB and also BC. So doing the sectioning will be step 3. Okay, and then step 4, draw the shear force and also bending moment diagram. So step number 4, so we draw shear force diagram, which is V versus X, and also bending moment diagram, which is M versus X. Okay, so that's the step. Okay, step number 1, draw free body diagram, and if you have the distributed load, you have to convert into concentrated load. And then step number 2, determine the reaction force. Okay, reaction force for this case is FA and also FC. And then step number 3, analyze each section, which is we have to do the sectioning for each section. And then step number 4, draw the shear force and also bending moment diagram. So please follow step by step when you are trying to draw the shear force and also bending moment diagram. So that is the procedure for method of section. Okay, now how to convert. Okay, so if you see from here, step number 1, convert distributed load into equivalent concentrated load. But how to convert? Okay, how to convert from distributed load to concentrated load. Okay, how to convert. Alright, so in order to simplify the analysis, distributed load can be represented as a concentrated load. So we represent distributed into concentrated load. It can be done by multiplying the distributed load by the length M. So what you have to do is you just multiply the distributed load value, okay, the magnitude of distributed load, by the length M. Okay, length M of it was distributed. Okay, it can also be determined by simply calculating the area of the rectangular. Okay, so now let's say you have rectangular distributed load. Okay, what is the rectangular distributed load? Means your distributed load looks like rectangle. Okay, so this is your distributed load, and then the shape of the rectangular, the shape of the distributed load is rectangle. Okay, rectangle. Okay, rectangle. Okay, so how to convert? You just multiply the distributed load, the magnitude of distributed load by the length. Okay, so means 5 times 6. Okay, 5 times 6 is 30. Okay, 5 times 6 is 30. Okay, so 5 times 6 basically is the area. Okay, the area. So this 5 basically is represented by one arrow, this height, and then this is the length. Okay, the length of distributed load. So 5 times 6, you get 30. Okay, or you can understand from here, this is 5 Newton per meter. So every meter 5 Newton. If you have 6 meter, so 5 times 6 go to 30. Okay, so 5 Newton per meter, every meter 5 Newton. So 6 meter, 5 times 6, so 30. Okay, so now we know the magnitude of concentrated load. okay, after converted from distributed load, okay, from distributed load to the concentrated load. So 5 times 6, so that's the magnitude. But where is the position? Okay, where should we put the concentrated load? Okay, so we have to put at the centroid. Okay, at the centroid for this. Let's say, for example, okay, let me explain. This is your distributed load. This one, distributed load. This is your distributed load. So I represent by this rectangle. So this is 5. This is 6. Okay. So when we convert, it's become. So that's your distributed load. And then we know that this distributed load can be represented by concentrated load. Okay, concentrated load. And then the value is 6 times 5, which is 30. Okay, so but where we should put that 30? Okay, where we should put the concentrated load? Here, here, or here? Okay, so the answer is we should put at the centroid. Okay, the centroid. For this case, the center of the triangle. Okay, so for example, you have triangle, and then that is the centroid. So the load must be acting, okay, through the centroid. Okay, so for example, this is your distributed load, and then that is the centroid for the rectangle. Okay, the center of a rectangle, and then the concentrated load. When you convert from distributed to the concentrated load, so that concentrated load must pass through the centroid. Alright. And then we have the second type of distributed load, which is the triangle distributed load. Okay, you have the triangle distributed load, which is here. Okay, which is here. Okay, so triangles mean half of the rectangle. Okay, so if you have rectangle distributed load, so triangle means half. Okay, triangle means half. Okay, half of the rectangle. So how to determine the value of concentrated load when we converting from distributed load to concentrated load? So you can get the magnitude of concentrated load by using half times 5 times 6. Okay, because 5 times 6 is the rectangle. Okay, so this is 5, this is 6. So you have multiplied by half, because rectangular is triangle is half of the rectangle. Or you can simply calculate the area. Okay, the area of the triangle, which is here is 6, and then 5 is here. So the area of the triangle is 1/2 5 times 6, so equal to 15. So you get 15. Okay, you get 15. And then this concentrated load must be positioned at the centroid. Okay, at the centroid of rectangle. Okay, center of the rectangle. So how to determine the centroid for triangle? Okay, if you have triangle, okay, let's say here is H and here is B, for example. So the centroid is located at B/3 and also H/3. Okay, H/3. Okay, so for our case, the H equal to 6 and the B equal to 5. So the B equal to 5, H equal to 6. Okay, so that's why the centroid, okay, the centroid is H/3, which is 6/3 equal to 2. Okay, so if we go back, that's why we locate the concentrated load 2 meters from end of the beam. Okay, so 2 meters from here. Okay, because this is the centroid. Okay, and then here is H/3, which is 6/3 equal to 2. and then you get 2 meter. Okay, so that's how we convert from distributed load into concentrated load and then position at the right location. Alright, so that is the equation for the centroid. Okay, for centroid for the triangle, and then that is the centroid for semicircle. Okay, so if you have a beam and then subjected to semicircle distributed load, semicircle's distributed load, so this is how you determine the centroid for the semicircle. Alright, and then the last type of distributed load is trapezium type. Okay, you see this is a trapezium type of distributed load. Okay, so if you have this type of problem, what you have to do is you divide into two parts. Okay, trapezium you divide by triangle distributed load, and also the other one here is rectangle distributed load. So this is the rectangle distributed load. So you have two parts here, two different distributed load, triangle and also rectangle. And then you just proceed, you just follow the same concept as previous. For the triangle, okay, you calculate you calculate what is the magnitude of the concentrated force, and then locate at the centroid. And then for that is for triangle, sorry, that for triangle. For rectangle distributed load, so you calculate the magnitude of the concentrated load, and also and then position the concentrated load at the centroid. So you will have two concentrated load. Okay, for the case of trapezium distributed load, you will have two concentrated load. Okay, this one is come from the rectangle. This one is come from the triangle of the distributed load. All right, guys, any question up to now? Any question? Any question? Guys, you alright?
Okay, sir. Okay.
Okay, good.